Hi, everybody. Welcome to the first lesson in the last unit of the year. This unit is called thermochemistry, or sometimes it's called thermodynamics. And this chapter is all about heat and energy. So when we talk about energy, those of you that are going to go on to take physics, you're going to talk about energy a lot in that class as well. And we talk about energy in sort of different ways depending on if you're in chemistry or physics. The definition where it says here, the capacity to do work, that is really more of a physics definition where you're going to be talking about like pushing a cart up a ramp and things like that. Whereas in chemistry, we talk about energy in terms of the word heat, and we're going to talk about how that energy is kept within atoms and molecules. So there are some laws that have to do with energy, and the first law of thermodynamics is that it is going to sound familiar to you. Law of conservation of energy is very similar to the law of conservation of mass. Energy can be converted from one form to another, but you cannot create or destroy energy. Okay, and in all honesty, guys, most processes that you witness in your everyday life are nothing more than one form of energy being converted to another. Okay. Anything that is electrical, anything that requires power is, requiring a battery of some sort. Batteries are little mini chemical reactions. A battery is nothing more than chemical energy being converted to electrical energy. Okay? Think of a nuclear power plant, for example. There's nuclear energy, all right, that changes to chemical energy, that changes to mechanical energy because steam is produced and it turns a turbine, and then that mechanical energy is converted to electrical energy. So there's lots of different types of energy out there, and we, throughout our everyday lives are usually converting from one form to another. Okay, so the energy of the universe, I know that's sort of a big thing to think about, is constant. So there's two types of energy. I mean, there's lots of types of energies, but the energies that we're going to talk about mostly in chemistry, there's primarily two types. Potential energy is the first type. In physics, you'll talk a lot about potential energy as energy due to position, like if you hold a bowling ball, and this is totally illegal, by the way, if you were to hold a bowling ball over the side of the Empire State Building, that bowling ball would have a great deal of potential energy. Okay, that's like a physics example, or like a body of water that is held behind a dam possesses a high amount of potential energy. When I was in physics, I thought a lot of potential energy as like the potential to do damage. In chemistry, we talk about potential energy as the energy stored in chemical bonds. Okay, for example, when you eat something like, a hamburger or a donut from Duck Donuts, yum. Okay, these are things that are loaded with saturated fat. Okay, and without getting into too many details, saturated fat is just long carbon chain molecules that all are single bonded to hydrogens. The point being, saturated fat is loaded with stored energy in those chemical bonds between all the carbons and hydrogens. Okay, there's a lot of energy stored in those molecules, and when you eat them, your body breaks it down in your stomach, and energy that was stored in those molecules is now released to your body, and your body can then use it to, go do whatever. All right, so in chemistry, potential energy is the energy stored within bonds. The other type we're going to talk about sometimes is kinetic. Kinetic energy is the energy of movement or motion. When you guys take physics, you're going to use this formula a lot. This is the formula for kinetic energy, 1/2 mass times velocity squared. Now, we don't talk about velocity much in chemistry. We are going to discuss kinetic energy in terms of temperature. In case you guys don't remember, the definition of temperature is the average kinetic energy. Okay, so when you raise the temperature of anything, a solid, a liquid, the gas in the room that you're currently occupying, when you raise the temperature, all you're doing is causing the particles in that room to move faster. That's it. Okay. These two words at the top of the slide here are words that a lot of people use interchangeably, and I want you guys to know that they do not mean the same thing. Okay, we just talked about what temperature is. Temperature is basically a reflection of how much are these particles moving. The faster they move, the higher the temperature is. Heat is not a measure of how hot or cold something is. Heat is a flow of energy from one thing to another. Okay? And heat will always flow from the hotter object to the colder object. Okay? Wherever you are sitting right now, if you're in your living room, your kitchen, your bedroom, wherever, I want you to just put your hand on whatever piece of furniture is closest to you. And you will notice that that furniture will feel cool to you. Okay? It isn't necessarily because it is cool. Okay, the temperature of the furniture in your, whatever room you're in is the same as the room temperature. But because our body temperature is higher, we are warmer than room temperature. When I touch the tabletop, it feels cold because heat is leaving my hand and flowing into the tabletop. And if my hand is losing heat, then whatever I'm touching is going to feel cold. Okay, so heat is a transfer of energy. Okay, we've seen these terms before, endo and exothermic. I just want to review them with you. Okay, it says heat exchange that accompanies chemical reactions. They can also accompany physical reactions as well. So let's just review. Okay, if we say that something is exothermic, that means that heat is being produced, heat is leaving, exiting, exiting this system. Okay? If heat is flowing into the system, then heat is being absorbed, or you can use the word required. That's endothermic. Okay? So you have this image on in your notes as well. Okay. Energy and heat are measured in units of joules and calories. Okay, those are just measurements of energy. So this nutritional label here, when we eat something and we read the nutritional label and we see that this whatever this is has 230 calories, that is a measure of how much energy this, maybe it's a protein bar or something, that is a measure of the amount of energy this food will provide to me when I eat it. Now, if you'll notice, up at the top of the slide, there's a conversion factor here. Okay, joules are probably the units we will use more often. But a calorie is another unit of energy, and that's the conversion factor. 4.184 joules is equal to 1 calorie. Please notice that the word calorie has a lowercase c. On the next line, the word calorie has a capitalized C. The calories that you see on nutritional labels are actually, they're like big C calories, they're actually kilocalories. So why do they do that? That means this, this bar, whatever this thing that I'm about to consume, doesn't actually have 230 calories. It actually has 230,000 calories. The nutritional community came up with this unit of the capital C calorie because they figured if you put on the label that something has 230,000 calories, nobody's going to want to eat that. So they created this new unit, and they didn't want to use the unit kilocalorie. So they just created this new unit of a capital C calorie. Okay. Just wanted you to be aware of that. I don't have it on my slide, but you have a second image in your notes that was taken from I think it's an apple juice label from Amsterdam. Okay, so it's not written in English, but you can see that the energy content is not written in calories, but is written in kilojoules. Okay. Over in Europe and many other countries around the world, they don't use the unit of calorie for energy. They use more often joules or kilojoules. So if you travel internationally and look at nutritional labels there, you may not see calories. You may see joules or kilojoules. All right. Okay. So this is kind of the main topic in this set of notes. There is a concept called specific heat capacity, and it's abbreviated with a capital C, sometimes a lowercase c. Let me define it for you, and then I want you guys to, try to understand it conceptually. It is the amount of energy needed to raise 1 gram of a substance by 1 degree. Okay, and what's in parentheses there, those are the units for specific heat capacity. So if you guys would, look at page 2 of these notes. There is a chart that lists all these different substances, and it gives their specific heat capacity values. Okay, each element, compound, whatever, they all have their own specific heat capacity value. These numbers are how much heat, it's the number of joules it takes to heat up these substances so that their temperature changes by 1 degree. So on the slide it says, what does it mean for a substance to have a small c value? So let's look at the chart here. And let's see which substance on there has the smallest, the least value. And it looks to me like that is gold. Okay. And its specific heat value is 0.13 joules per gram degrees Celsius. So what does that even mean? Well, guys, since that's the smallest number on the chart, that means it does not take much energy to heat up gold. Adding just a tiny little bit of heat to, let's say, a gold ring will make its temperature change pretty dramatically. Let me say it to you in another way. Gold is very easy to heat up. And if you'll notice, the metals that are on this chart in general have low specific heat capacities. Aren't metals good conductors of heat? Question mark? Yes, they are. Okay, so things that are very good conductors tend to have very low specific heat capacities. They're easy to heat up. Okay, What does it mean for a substance to have a large specific heat capacity? If you'll notice on this chart, liquid water has the largest value, 4.184 joules per gram degree Celsius. So that means it is very difficult to heat up water, and vice versa, to cool it down as well. If you have a very hot sample of water, it will take a long time for it to cool down. So water is not easily heated up. Water is also not very easily cooled down. So think about it, guys. What is the opposite of the word conductor? If a substance is a poor conductor, which water is, it's an excellent insulator. So materials that have high specific heat capacities, meaning they do not heat up quickly or very well or easily, and they don't cool down easily either, those are good conductors. Okay, so you'll have some questions over in the homework that kind of answer that ask questions about that concept of what does it mean for a what does it mean for a substance to have a small specific heat capacity or large. Now, we're going to take this concept of specific heat capacity and we're going to put it into a formula. Okay, and I know there's a lot in front of you, but it's written a little bit more succinctly in your notes. There is a formula, and I want you to focus your attention right here. Okay, Q equals mc delta T. This is an equation that we're going to use if I say to you, this amount of heat is applied to a swimming pool with this amount of water in it. Here's the specific heat capacity for water. How much will the temperature change? Okay, so let's define what these variables even are. Okay, Q stands for heat, all right, which could be in calories or joules. Typically it's going to be in joules though. M is mass in grams of whatever substance we're dealing with. Okay, C is specific heat capacity. Delta T, delta always means change, the change in the temperature. Okay, and if you'll look right here, I want you guys to always calculate delta T as final minus initial. Okay, whatever the final temperature is minus the initial, even if that gives you a negative delta T, and we'll talk about what that means. Okay. Now, at the bottom of the slide here, it says make sure to memorize this. Obviously, since we're in this virtual learning, you don't have to memorize anything because everything's open note. But those normally would be values that I would want you to commit to memory. That water, liquid water, because solid and gas have different values. Liquid water's specific heat capacity is 4.184 joules per gram degree Celsius, or an easier number to remember, 1 calorie per gram degree Celsius. Okay, so let's look at an example problem. This is the same one you have in your notes. It says, how much heat energy is released to your body when a cup of hot tea containing 200 grams of water is cooled from 65 degrees Celsius to body temperature, which is 37 degrees Celsius. So if you drink a cup of hot tea, it's going to eventually, all of that liquid that you've consumed is going to cool down from the hottest temperature that it was. Now that it's in your body, it's going to cool down to the same temperature as your body. How much heat has been released to your body? So if you look, we do mc delta T. We plug in the mass of the water, the specific heat capacity of the water, and then look at what's in parentheses at the end. Final, 37, minus initial, 65. Okay? Round for significant figures. Q is equal to negative 23,000 joules, which you could leave it like that, or if you want to shorten it, you could shorten that to negative 23 kilojoules. Okay? Now, you'll notice, guys, that our answer in this example problem is negative. That means this releasing of heat, because think about it, this water was very hot and then it released the heat to our body. When heat is released, when Q is negative, that's an exothermic change. Okay? And this is really silly, and maybe I've said this before in class, I can't remember. Okay? But a way to remember that negative heats are exo, think about it this way. We tend to think of our ex-boyfriends and girlfriends in a negative light. Okay? That's why they're exes. Because we don't think of them positively, we think of them negatively. Okay? I know that's silly. All right, so if Q comes out negative, whatever just happened must have been an exothermic change. If Q comes out positive, then it's an endothermic change. Okay? So what I want you guys to do now is to pause this video and complete the questions just in part 1 under where it says homework. Check your answers and then come back. Okay, so this next section has to do with phase changes. So you're going from solid to liquid, or liquid to gas, or gas to solid. Okay, we're changing the physical state. Heat is either absorbed or released in these processes. Okay, these are not chemical changes, these are just physical changes, but they can still be considered endo or exo, depending on if heat is absorbed or released. All right. Now, we'll get into this more 2 lessons from now, but when you are going through a physical change of state, okay, you're melting something, you're boiling something, the temperature does not change, okay? When you are melting a block of ice, the temperature stays at 0 degrees the entire time until that whole block is melted. When you're boiling a pot of water, the temperature of the water is 100 degrees, exactly, and it does not change until all of the water is boiled away. But we'll talk more about that later in a couple of lessons. Okay, so, but energy is being added or released in these processes. I mean, I said up top, these are endo or exo, situations. So what is the energy doing? If the temperature isn't changing, what is that energy doing? It's being used to break bonds. When you boil a pot of water, the energy from the stove is being used not to change the temperature, not to make the particles move any faster, because that would be changing the temperature. It's being used to break the intermolecular forces between the water molecules. And that requires energy. Okay? If you're going the other way, if you have a Okay, sorry, I got a little distracted there. So here's the thing. If we were changing the temperature, okay, let's remember what the definition of temperature is. Temperature is the average kinetic energy. When you go through a phase change, you are not changing the temperature, so the kinetic energy is not changing. So what must be changing is the potential energy. Remember, we said that potential energy is what is stored in chemical bonds and intermolecular forces. So if you're changing those, then the potential energy is changing. So actually, before I do that, so what I would like to do, if you guys will go over to the homework questions, go over to part 2, where you see all these arrows and it says solid, liquid, gas. Okay, remember that solids have the lowest amount of energy content, liquids have a little bit more, gases have the most. Okay, so the first thing that you're asked to remember here is what are the names of these phase changes? Okay, so let's see, number 1, actually I'm going to go out of order here. Okay, so solid to liquid, that's arrow number 4. You can call it melting. It's also, if you want to be fancy, that's called fusion. All right, from liquid back to solid, arrow number 1. Okay, you could call it freezing if you want to be fancy, that's crystallization. Liquid to gas, arrow number 5. You might call it boiling, okay, but if you want to be fancy, it's vaporization. Gas back to liquid, condensation. Solid to gas, so that's arrow number 3, is sublimation. Gas back to solid, the one that most people don't remember, the one we talk about the least, is deposition. Okay, now, the way that the words solid, liquid, and gas are arranged on your paper are not great, okay, but look up at the screen here. Solid has the lowest amount of energy, then liquid, then gas. Any phase change that's going in that direction, so solid to liquid, liquid to gas, solid to gas, you're going from a low energy state to a higher. Those are going to be endothermic changes. Any phase change that's going from gas to liquid, liquid to solid, gas to solid, you're going from a higher energy content to a lower. That's going to be exo. Okay. So I wanted to sort of go over that with you. So there is a concept, okay, that we need to talk about. So let's get to the calculations part of this, and we'll weave the concept into it. If there's no temperature change during a phase change, then we can't use that same equation, mc delta T. All right, we have to use something else. So what we use, still Q, we're still calculating heat, but there is no delta T here. It's actually a simpler formula. It's going to be Q equals mass times something called the heat of fusion, which is a number that you'll use if you're going from solid to liquid or liquid to gas. You can use it in either direction. Or you'll use the second equation. Heat is equal to mass times the heat of vaporization, which is the number you would use if you're going from liquid to gas or gas to liquid. The only reason I don't have a third equation going between solid and gas is because that just doesn't come up very often, so don't worry about it. So heats of fusion and heat of vaporization, these are numbers that will be provided to you. If you look at the chart on the second page of your notes at the very bottom, you'll see words like melting, freezing, vaporization, condensation. Which of these concepts, heat of fusion or heat of vaporization, which one would you use depending on which direction you're going? Like, are you going from solid to liquid or are you going liquid to solid? Changes whether the process is endo or exo. Are bonds broken or are bonds being formed? And then if you look at the values at the end of the table, you'll notice that for any process that is endothermic, where we're breaking bonds. Okay? The values are positive because they're endo. Whereas any processes that are exo, where you're forming bonds, those are negative. Okay? So you have 3 examples in your notes. This is the first one. Okay? It says, calculate the amount of energy needed to melt 5 grams of ice at 0 degrees. Okay. There's not 2 temperatures. There's no delta T here. All right, so here's the equation we're going to use. Heat equals heat and a little FUS. That stands for fusion. Now, why did I choose heat of fusion? Because the process of melting is between solid and liquid. Okay, so I don't want to choose heat of vaporization. I want to choose heat of fusion times the mass. Where did I get that number 335? I got it from the chart on the previous page. That's a number you do not have to memorize. And I made it positive because the process of melting is endothermic. Multiply them together, grams cancel out, round for significant figures, and that's the number that I get. Notice it is positive. It's an endothermic process. Okay, if we asked the exact same question, but going the other direction, here's how it would be phrased. Calculate the amount of energy released to freeze 5 grams of water at 0 degrees. The calculation would be exactly the same, except my final answer would come out to be negative. The process of freezing is exothermic. Okay? So I have given you all the tools that you need here to now finish up the last 2 pages of these homework questions, so you can do parts 3, 4, and 5. Some are short answers, some are multiple choice, some are free response, and you can then check your answers, and I look forward to seeing you guys at the next lesson. Take care.